I didn't have a good segue from the spiritual thought to the material, so whatever. Amen. Yeah, that would have been a good one. Last time we talked about PLP-mediated transfer of amino groups, turning alanine into pyruvate by transfer of the amino group from alanine to alpha-ketoglutarate. We did that for aspartate 2. We showed how your body basically shuttles amino groups around. And at the end, we started to talk briefly about neurotransmitter synthesis. And we wrote an example of that in the case of the function of the enzyme histidine decarboxylase. And what I wanted to do was just walk through that mechanism together. I've drawn out all the intermediates, so all you have to do is supply the arrows. The reaction starts with the amino acid histidine. Where's the... There we go. Starts with the amino acid histidine and the cofactor PLP, which is, I always forget, it's vitamin B6, right? Yeah. And you form the imine. We went through that several times last time. Remember, you get the imine by bonding the nitrogen to the carbonyl carbon with a double bond. And then the thing that ends up leaving is H3O+. So this is the imine. You don't have to know the mechanism for imine formation. You do have to be able to predict the structure of the imine. That's not the point of this question. I've done that for you. What I want you to do is show how the elimination occurs. In the mechanism, you go from this imine to this intermediate and CO2, and then you get another imine. We called this mechanism does not involve the tautomerization that we talked about yesterday. You will see that before and after loss of CO2, the imine is on the same carbon, and then when the imine gets hydrolyzed, you end up with this version of the amino acid that lacks the acid. It's just the amine, and this is the molecule histamine. Histamine's an interesting molecule, and we'll talk about it after you've done the mechanism. But go ahead and get started on that. I want you to start here, because again, you don't have to know about imine formation. I just want you to start here, show the decarboxylation mechanism, and then show the proton transfer, and you're going to end here. I expect you to be able to predict the products of imine formation. I also expect you to be able to predict the products of imine hydrolysis, but don't worry about the mechanisms of those reactions. If you want to see it, I can show it to you sometime, or you can come to my office and talk about it, but I'm not going to ask you to do that here. All right, go ahead and get started. Yes, because yesterday when that happened with the carbonyl, yesterday when that happened, okay, do you remember yesterday the difference between the albumin and the ketamine? The
There's no way you put something this line up wrong exam, that's why.
Okay, so. Okay, there have been a couple of questions. One is somebody was asked at the stage, and this doesn't ask about the mechanism, at the stage of kidney hydrolysis, folks notice that PLP is just itself with the oxygen on the carbonyl carbon and the nitrogen still on histamine. Yesterday, when we used PLP, that didn't happen. The reason that didn't happen, if you remember the difference between the aldimine and the ketimine, the aldimine is the imine you get from the aldehyde of PLP. So this is the aldehyde of PLP. That's the carbonyl carbon. I'll just highlight it here. That's the carbonyl carbon in the aldimine. Notice that in the reactions we did yesterday, there was a tautomerization step that changed the carbonyl carbon to over here, and then you got the ketimine. We're not doing that here, and so the carbonyl carbon stays on the same carbon, and that's why when you hydrolyze the imine, you get the aldehyde back. Yeah, another question.
When you say predict the product, are you just saying where you have to start here, just know that that's the product?
So start here means for mechanism.
Yeah, but then
What I'm saying is, and it's sort of a reference to what we did yesterday, if I gave you these two things and said form the imine, I'd expect you to be able to draw this without help.
Okay, and then for elimination.
Same for the elimination, you should be able to draw the mechanism. For proton transfer, you should be able to draw the mechanism. Imine hydrolysis, again, you should be able to predict the product with no help. But not the mechanism here. Yep. Okay, so some comments are this is deceptively simple. And I said, getting cocky, are we? No, actually, I should have said in Vader's voice, impressive, most impressive. Obi-Wan has taught you well. Except in this metaphor, I am both Vader and Obi-Wan, which is kind of cool. So anyway, somebody want to show us mechanism, talk us through it? A couple of arrows. Was that a volunteer or you were just waving at us? Okay, Amber, come on down.
Don't mess up.
We're going to see her attacking the histamine at the bottom.
Oh man.
I turned off the weird eraser thing, so if you need to erase, it should be fine.
Okay, perfect. Okay, so you take the lone. Oh.
It's on laser pointer now.
Oh, that makes sense. Is it this one?
Yep, you
Okay.
got it. Change color, whatever you want.
Okay, so the lone pairs on the oxygen. You'll take these and attack this bond, and then you'll take the electrons and move them to the carbon. So, and then it eliminates the carboxylate off of the thing and makes CO2. And then you'll take the electrons up to this hydrogen, and then the electrons will move onto this A enzyme.
Okay,
That's it.
good. Excellent. Thank you, Amber. Bravo. 4 more years. Good. So, in how we've talked about carbonyl chemistry for a long time, you can think of this as a carbonyl carbon, this as the kicker offer, and then all of this as the leaving group. So the oxygen on the CO2, the negatively charged oxygen on the carboxylate, is kicking down to eliminate the leaving group, and the electrons from that carbon-carbon bond are going on to what we have called the alpha carbon. So that's good. And then, of course, afterwards, we protonate on the alpha carbon. That gets us to this neutral, or at least neutral on that carbon molecule. And then imine hydrolysis gets us to histamine and PLP. Okay, questions about that? Okay, so I have asked, actually, I didn't realize this, but I asked a question about this on the first exam. It was a question about resonance. And I believe the question was, which of the following are valid resonance structures of this intermediate, which is the good leaving group? Now, it was a little different because I used a different amino acid. It was dopamine synthesis instead of histamine synthesis. So I've been doing this the whole time. Now you know my evil tricks. Well, I want us to reflect for just a minute on why the decarboxylation can happen. Essentially, the decarboxylation can happen when the carboxylate is attached to a good leaving group. That's the pattern. What makes a good leaving group? Generally something, at least in biology, generally something that is resonance stabilized. So I'd like for you to demonstrate to me that this intermediate with a negative charge on the alpha carbon is indeed a good leaving group by drawing 3 resonance structures, and on one of them, I'm going to specify there's more than 3 that you could draw. On at least one of them, I want the nitrogen in the ring to be neutral and have a lone pair on it. Okay, so yesterday we were loathing having to draw the PLP group. We are going to do it again. You complain about it too much, and this is what you get. No, this is good practice, and this will be a way for you to assess how much you've learned since that first exam, especially if you got that resonance question on the first exam wrong. If you need help, remember the simplest way to convert one resonance structure to another is the negative charge 2-step. That is, lone pair adjacent to a pi bond. You can always move the lone pair over to become a pi bond, and then move the pi bond over to become a lone pair. Then draw that structure, and then do it again. you doing? You got one? You got two? Anybody got questions? Yeah.
Yes, it is. You would need to also, if you're gonna do that, put the double bond between this carbon and this nitrogen. So this arrow should go from the lone pair to the bond to the space limit pi bond. Yeah. Let me look at it. So the thing that's not right here is that you've got too many bonds to nitrogen. So this bond is fine. If you're gonna do that, you have to move this bond onto the adjacent carbon. That's what I was talking about for the two step. Yeah. No, that's great. That works totally. You just done a lot at once, which is fine. Totally fine. You can keep track of it. It's always easier to take this lone pair, move it. Oh, I can't do this upside down. Always easier to take this lone pair, move it over to form a pi bond here, but if you stop there, you got too many bonds to nitrogen, so you take this pi bond and move it to that atom. 2 arrows. Yep. So starting from here. Yeah, that's a great resonance structure. Your starting structure there was. I think it's confusing because there should have been a negative charge there. And there should have been one there.
Yeah, this is, that was me.
Right. So this is just a note to yourself to show you that that's not wrong. Typically, structures that way. Each resonance structure has a resonance structure on its own. Besides the charges.
Okay, we need 3 volunteers for this one. I asked for 3 resonance structures. So I'd like to invite individuals to come forward and draw their resonance structure. Is that a volunteer or a question?
No, I can do it.
Was that a question? No, okay, come on down. I know, Andrew, I needed 3, you're next. We were gonna do it one by one, but yeah, that's fine. Come on down, whichever one you want.
I've been practicing hexagons recently.
And don't be shy if I'm a stickler about charges, it's just gonna help you get questions right. Nice. Can you fill in for me the
All right.
remainder of the double bonds in the
Mouthful.
ring? Thank you, thank you. There you go. All right. Very nice. Looks good. Well, no. Go ahead. That's fine. Here are the arrows you would use from this top structure to get to that resonance structure below. You start with the lone pairs on the alpha carbon. You make a pi bond with the adjacent atom. That you know that's possible because that adjacent atom is involved in a pi bond itself. But if you stop there, you'd have too many bonds to nitrogen because the nitrogen already has a lone pair. And that would be 5 pairs of electrons around nitrogen. So you must break the other nitrogen carbon pi bond. Where's it going to go? You could do a couple of things with it, but the easiest is to simply put it on the other atom that was involved in the pi bond. That's what I'm talking about when I say negative charge two-step for resonance structures. That's the easiest and simplest way to convert one resonance structure to another. We could have done something more complicated and we could have got it right, but this is a way to do it step by step so you know what to do. Okay, Ange, you're up. Oh, also when we're drawing resonance structures, we use a double-headed arrow like this to communicate that the two things that we've drawn are actually resonance structures of each other. All right, go for it.
Do you want me to just draw this product, or
Sorry, what?
do you want me to just draw the product?
Yeah, just draw the resonance structure.
Okay.
Good.
Yeah.
Yep.
That's it.
Good, so you've abbreviated the histamine part of the molecule, and you've abbreviated that phosphine side chain on the ring, that's totally fine. That's a valid resonance structure. Now for bonus, can you devise some arrows that would get you to that from the first resonance structure that's shown underneath 2?
The first one that was drawn?
Yeah, just use, draw some arrows that would allow you to get to your resonance structure from there. Good. Great, so that's using 4 arrows, and that's jumping ahead. Great. Alternatively, one way to do this would have been, if you wanted to, you could generate a resonance structure where instead of moving this pi bond over to form a pi bond between these 2 carbons, you would have simply moved the electrons from that pi bond onto this carbon with a negative charge. So that's, going from here to here is sort of 2 arrows. Ange jumped ahead with 4 arrows to get the negative charge over here, but if you could also have done 2 arrows. Those would have both been great resonance structures. Great. Very good. And lastly, yes, thank you. This isn't like the ice bucket challenge where you can nominate somebody. I told you, right, that my 14-year-old is this was 10 years ago, like when you guys were in middle school or something like that, the ice bucket challenge was a thing. They're trying to resurrect it. And the 14-year-olds are getting their dads to nominate each other. I got nominated, but I haven't done it yet because I think it's unpleasant. Why would I do that? Although maybe on the last day of class, we should just have you guys all dump the water over me, kind of like a Gatorade coach moment.
I'm so dumb.
I've seen a lot of failed ice bucket challenges on the internet because water's heavy. Drop the bucket on the head or drop the water on themselves. Oh, I was gonna, at bonus points, I was gonna say start with Angie's structure and do arrows to get to yours, but you did that. Great, perfect. Well done. Very nice. I think that's good enough. Thanks. All right, so the point here, two points. First, basic skills for converting resonance structures from each other. Arrow two-step, you could do more than 2 arrows. If you're a little bit nervous, stick with the 2 arrows and just go one resonance structure to another, walking the charge around the molecule. Second skill is recognizing when you draw a resonance structure if you've got something wrong. All resonance structures must be correct Lewis structures. No more than 4 pairs of electrons around a second row atom like carbon, nitrogen, or oxygen, and you got to have correct formal charges. Go ahead.
So I have a question. Is nitrogen positive and when is it neutral or negative?
Yeah, nitrogen. Oh, sorry. Yes, one minor thing here. The nitrogen should be neutral there. It was written as positive charge. It needs to be neutral here because it owns 1, 2, then 3, 4, 5 electrons, and nitrogen normally comes with 5. So when a nitrogen has a lone pair and is bonded to 3 things, it is neutral. When a nitrogen is bonded to 4 things with no lone pair, it's got to be positively charged. Yep, great. All right, what else? Yeah.
So I remember you talking about resonance, how the formal charges are always the same.
Yes.
Like they always kind of
Add up to the same.
Yes. So is that why? Because both of those structures they have 1 positive and then 2 negatives, so it'd be basically negative for both of them. And
Yes.
then this one only has 1 negative sign, but not another positive or negative, so it would be negative, and that's how.
Yes. Yeah, so the rule is the overall formal charge can't change, but as long as the overall formal charge stays the same, you can create new pluses and minuses. So notice, for example, for the first resonance structure, minus plus minus, net 1 minus. Over here, minus plus minus, net 1 minus. Over here, just minus. But it's all fine. Yep, great. Importantly, one of the things you can realize about this leaving group, we've demonstrated that it's resonance stabilized. The other thing we've demonstrated is this nitrogen that there's one resonance structure in which this nitrogen that used to be positively charged is neutral, and none of the carbons are negatively charged. This is a really important resonance structure, and it demonstrates why PLP enables the decarboxylation, because it turns what's bonded to the carboxylate into an excellent leaving group. That's why the decarboxylation can happen. Okay, questions about that and resonance structure? So let's just say a little bit about histamine. You've heard about it before. Likely you've heard of antihistamine. So histamine is a neurotransmitter and a signaling molecule. It's involved in a lot of different things. In the immune system, it's involved in allergies and inflammation. So it's stored in molecules called mast cells and basophils, and it's released in response to injury or an allergic reaction. And what it does is, in the case of injury or allergic response, it increases blood vessel permeability. It makes blood vessels leakier. That causes redness and swelling, itching, and even causes increased mucus production and runny nose. So by increasing the permeability of blood vessels, water sneaks out of your blood vessels, and then if you're like me and you're having an allergic response, your nose starts to drip, and that's because the histamines have made it. You're not bleeding. Blood cells are not getting out, but water from your blood certainly is. So that's the target of antihistamine medications to prevent that from happening. They work pretty good, except that histamine is also involved in the nervous system, where it regulates alertness, sleep-wake cycles, appetite, and body temperature. So if you take certain antihistamines, especially the first generation ones like Benadryl, and we'll talk more about these when we talk about mechanism of drug action, you can get sleepy. And I tend to have bad allergies. I have for a long time, and there are days when it's not decent for me to come out in public if I don't take an antihistamine because the nose is just dripping. Like, it's gross. I'm sorry that we're talking about it. So one Sunday I took not one but 2 Benadryl, and 2 Benadryl is like, you're not going to have a runny nose anymore, but you're also not going to be very alert. And I was playing the organ that day in sacrament meeting, and it was all I could do to maintain consciousness and focus on the notes. It was somewhat out of body experience as we were playing the music. So don't recommend that. I also don't recommend driving while taking Benadryl. And Tylenol PM is just acetaminophen with a little bit of antihistamine in it. The way it makes you sleepy is it's an antihistamine, and antihistamines make you sleepy. It's also involved in the digestive system, regulates stomach acid. It can be important in exercise recovery. So pretty important molecule made by a pretty simple mechanism from a pre-existing amino acid. There are 3 other neurotransmitters that are made by this pathway that are important too, and they're on the back of your quiz. Here, you're going to predict the products. All of these reactions happen by the same mechanism that's shown in question 1. Question 1 shows you PLP-mediated decarboxylation of histidine. To get histamine, you lose the acid group as CO2, and what's left is the amine portion. So take what you learned from question 1, and I want you to predict the products that come from the amino acid L-DOPA. This is a version of tyrosine. It's been oxidized to have an additional OH group, and it's going to get decarboxylated to form dopamine. This is 5-hydroxytryptophan. It's also been oxidized by an enzyme to put an OH on the benzene ring. This is going to be decarboxylated to form serotonin. And then this is glutamate, which is going to get decarboxylated to form gamma-aminobutyric acid, or GABA, which is another neurotransmitter. So go ahead and see if you can predict those products based on what you know about decarboxylation. If you need a reminder, PLP is going to make an amine with the amino group, turning all of this into a good leaving group, and then an elimination reaction is going to happen. Okay, you tell me what to do. So decarboxylated, the whole thing except for, okay, and then NH3. Right, and we'll draw, because I put PLP over the arrow, remember PLP makes this process happen, but at the end it goes, you get imine hydrolysis. So for all of these reactions, we're starting here and we're going all the way here, and I'd like to see the amino compound that you make. So there is dopamine. That's what it looks like. Now you've heard about dopamine's in the pop culture. People will say, oh, I need to get a hit of dopamine. Somebody recently was telling me that they call their niece or their grandbaby sort of a bundle of dopamine because you hold the baby and you feel good. Dopamine is involved in some of those things. It's known as the feel-good transmitter. Lower levels of, oh, sorry, that's not dopamine, that's something else. I got that one wrong. That was serotonin. Dopamine is involved in motor control. And so a dopamine deficiency is linked to Parkinson's disease, where people start shaking and as part of a neurodegenerative disease. It's involved in motivation and reward, so it is released in response to enjoyable activities. For example, holding a little baby. I've got a niece that's like maybe 2 or 3 months old, and she just randomly falls asleep on your shoulder. It's just the best thing. A lot of dopamine there. Yeah, go ahead.
Do you want us to show the lone pair?
Lone pair. Oh, right. So I'd like to see the final product, which happens after that lone pair gets protonated. Yeah. So not just after the decarboxylation, but protonation, which also happens in the enzyme active site to give you that product.
And so then it's not one dash anymore, it's just, does that?
Right, you could use a wedge or a dash, but this is no longer a stereo center, so it's not necessary. The fact that this is a carbon attached to 4 different things tells you that it's tetrahedral. If you wanted to use dashes and wedges to indicate 3-dimensional structure, that's fine. They're not mandatory because it's not a stereo center. Also, because you can rotate freely about sigma bonds, it's fine if you draw the nitrogen over here. Let's see, dopamine's also related to reproductive hormone balance and cognitive function. So motivation, reward, and cognition. Serotonin is going to be basically the same thing, a benzene ring. You're just going to keep everything about the molecule, only in place of the CO2 group, you're going to put a proton. Because the CO2 group kicked off everything else. There used to be a negative charge on that carbon, and then it picked up a proton. And you can, if you're drawing this as it would appear at physiological pH, it would be positively charged. So that's serotonin, also involved in mood and emotion, known as a feel-good neurotransmitter, and low levels of serotonin have been associated with depression and anxiety. So serotonin is the target of the so-called SSRI class of mental health medications. That stands for selective serotonin reuptake inhibitors. We will talk about those more when we talk about drug action, but basically they increase the levels of serotonin in your brain by inhibiting the receptor that takes serotonin from the synapses back up into the neurons. An example of an SSRI is called sertraline. It's got an amino group on it and a benzene ring, and then a second benzene ring. Oops, I needed a little bit more space. There we go. A second benzene ring, and the second benzene ring has a couple of chlorides on it. So that's sertraline. And this one I actually take. So maybe 10 or so years ago, I had some anyway, I told you before that for most of my adult life, I've sort of struggled with a little bit of religious scrupulosity, a little bit of depression, a little bit of anxiety. And I started, on the advice of my primary care provider, started on an SSRI, sertraline, and it was going pretty well for a while. In fact, I adjusted enough that I didn't feel like I needed it anymore, so I tapered it off. And then, surprise, symptoms came back. When you stop taking your meds, the symptoms come back. So I started on it again. One of the things that I noticed when I'm first going on this med, they tend to have you start with a low dosage, 25 milligrams or so. And the reason for that is there are side effects, which include, this is bizarre, it's called bruxism, it's jaw clenching. So when I first, I don't know why it happens, maybe it's on the list of serotonin's activities. It's a known side effect. When I first started on the med, when I was eating cereal the next day, I'd be like, man, this is really hard chewing the cereal. My jaw is exhausted. And it actually is. It tends to, maybe it makes you smile all the time. I don't know. You're smiling and your jaw's clenched or something like that. So that was a weird thing to get used to. In the process of going off it and then coming back on it without a physician's advice, my dose had been increased. Is this TMI? You guys care? You want to know about this? My dose had been increased to, I think I was finally taking, my maximum dose was around 200 milligrams, which is a little bit, which is a lot. And I tapered off and then decided I probably need to start this again. So I took a 100 milligram pill, and then that night, first 2:30 in the morning, I'm wide awake and I can't go back to sleep for another couple hours. I was so angry. I realized that serotonin is also involved in sleep-wake cycles. It's a precursor to melatonin, which is the sleep hormone. So if messing with serotonin in your brain can mess with sleep cycles. I was angry and I decided I'm not going to do that again. So that increased the amount of time I was without the meds. I finally, talking to my primary care provider, he's like, dummy. He didn't say that, but maybe he did. He kind of resents organic chemistry professors. Dummy, you should start out with a really small dose and then we'll gradually ramp it up. So going back on it this year has actually been totally easy. Started with the 25 mgs and now I'm up to 50 and symptoms are okay, doing fine. So anyway, these things adjust, but these things require adjustment, but we'll talk about some other drugs that do this as well. And it's quite fascinating. Okay, lastly is GABA, gamma aminobutyric acid. And again, once you get it, this kind of question is easy. All you do is you draw the rest of the molecule without the CO2 and a proton in its place, and that gives you GABA. GABA is involved in it's an inhibitory neurotransmitter, so it reduces the activity of overexcited neurons, promotes relaxation, reduces anxiety, can promote sleep. It is the target of sedative drugs like barbiturates, and low GABA is associated with some anxiety disorders. It's sort of called the brain's brake pedal and supports relaxation. Okay, so that sort of concludes our PLP efforts to understand amino acid metabolism and what amino acids can do. Let's take a break, and when we come back, we're going to practice your amino acid structures by drawing these Star Wars themed peptides as they would appear at physiological pH. So let's take a break and we'll be back in about 5 minutes or so.